Hi there, I'm Natalie Nicole Sanchez, a graduate student at the University of Washington working with Jessica Work, and I'd like to share the results of my recent paper, Two Quench, which explores quenching in Milky Way-mass galaxies through minor merger interactions. To begin, I'd like to introduce our simulation suite, the Pioneer GMs. From an initial 50 megaparsec dark matter only volume, we selected a Milky Way-mass galaxy with an LMC mass galaxy at z equals 0 as our reference. We ran a zoom-in simulation of this reference using the SMBH code Changa and included subgrid models for star formation and feedback, as well as updated prescriptions for black hole physics. Then we used the genetic modification process of Roth et al. 2016 to create 3 nearly identical initial conditions of our galaxy, which maintain the large-scale structure and final main halo mass of the original, while allowing for slight modifications to the accretion history. For this sample, we systematically shrank the mass of a satellite galaxy to produce 3 genetically modified galaxies. As you can see from the star formation history on the left, the small modification of the satellite resulted in very different baryonic evolutions. Patient 0 and GM1 in blue remain star forming to z equals 0, while GM2 and GM3 in red fully quench by z equals 1. Again, these galaxies are based on nearly identical initial conditions, so the differences between their baryonic evolution, though not unexpected, brings us to the driving question of this paper. What drives the quenching in these galaxies? If we look at some of the properties of the galaxies, we don't see significant differences prior to the time of quenching at z equals 1. The stellar mass, total gas mass, and cold gas mass in the halo and the disk are not significantly different prior to this time. What is different is that each GM galaxy experiences a series of minor mergers at z of 1. Due to the GM process, the timing and sequence of these satellite interactions is changed between the star-forming and quenched cases. In the star-forming case here on the left, satellite 1 does a flyby of the main galaxy first. This interaction is followed by a flyby of satellite 2, which then turns around and merges. And finally, satellite 1 merges last. In the quenched case, however, satellite 1 still begins with its flyby over here to the right, but then it merges right before satellite 2 does its flyby. This double interaction is then followed by a significant outflow, which you've just seen, and finally, satellite 2 merges as well. Here is a diagram to show this interaction in more detail, and I'm focusing on the interaction in the quenched case. The combination of satellite 1's merger and satellite 2's flyby, shown here at the center, are key in explaining why we see such a significant outflow and subsequently why these galaxies quench. First, satellite 1's merger, noted by the solid red triangle, provides fuel to the supermassive black hole, resulting in a peak of supermassive black hole accretion within just a few hundred megayears. Then, the combination of satellite 1 and satellite 2 work to disrupt the angular momentum of the cold gas in the galaxy disk. Here, we see the angular momentum of the gas scaled by the total angular momentum of the disk. So prior to the interactions, both cases have gas more in line with the disk's angular momentum, or close to 1, while in the quenched cases, post-merger, the gas is dispersion-dominated, or close to 0. Finally, immediately following the interaction, the supermassive black hole peak in accretion, and the disk's disruption, a large-scale outflow quenches these galaxies. Which brings us to our conclusion that, in short, to quench these galaxies, it is the combination of fuel given to the supermassive black hole by satellite 1 and this disruption of the main galaxy's disk by both satellites' interactions which result in the supermassive black hole-driven outflows that are strong enough to quench the galaxy until z equals 0. Now you might wonder how rare this type of event is, and I encourage you to check out our findings in the paper to answer this question. Thank you very much.